Analysis of doubly reinforced flange beams is similar to doubly reinforced rectangular section beams. The only change you find it in flange beams is the shape of the beam. Right? So let us take a T-beam. Of breadth BF, breadth of flanges BF, depth of flanges DF, this is breadth of web, and if you have area of steel in tension from say center to the top fiber, we will denote with a capital letter small d. This we are representing with ASD. In doubly reinforced, we also have ASC contributing to the moment of resistance. So when you have an additional material there, so the stress strain diagram will not change that much, but rather another force value will come. Right? I'll draw this stress strain diagram. The stress strain diagram of doubly reinforced flange beams is very similar to rectangles. So first we will draw strain diagram, then we will draw stress diagram. So let us take XU as neutralizes depth, and let me take this as neutralizes depth. Now we have here a strain of 0.0035 following to 0, then we have here a strain of should not be more than or equals to 0.87 F5 by ES is 0.002. This is stated as ultimate strain in steel. This is stated as ultimate strain in concrete. Now there comes an area or strain value where it is 0.002. So why we are plotting this 0.002 means? Now if you take a look of the stress diagram, at 0.002 up to 0.002, the stress diagram will be rectangular. Then afterwards, a parabola starts. So this value we know it as 0.45 LCK, and you have a force which is acting here, and you also have a force acting here. Two forces are acting. Fine. Now, as because the steel is there here, we also have got another force which is coming from steel. So let me take this as the center point of it. So this would be this thing. The force which is coming from the material which is in compression, right? So this is compression force, this is compression force, this is tensile force, right? So this is TU ultimately we will say, and we will denote this as compressive force of steel and compressive force of concrete, you represent centimeter, right? And if this is HCU and if this is total D, this would be D minus HCU. And next, we also know that this force acts at a distance of 0.42 x cube. It acts at a distance of 0.42 x cube. And from the code we also know that this force is given by ultimate force of concrete in compression zone from code book. It is given as 0.36 FCA into B times x cube. Now I have not written here a BF or BW because it depends upon the neutralizer. So let me just put BX. And the force due to steel is given by FSC. This is the force value and this is the force value, and this value is given by 0.87 F into H. Now if we note these force values by variation of neutral axis, we can easily evaluate the moment of resistance. Considering equilibrium of forces, considering equilibrium of forces, that is total compressive forces equal to total tensile forces. That implies we have a force of 0.36 FCK B times XU plus we have a force of FSC into ASC. We have another term which is the force coming from the flange, which is given by 0.45 FCK BF minus BW into, let me take, it depends upon whether it is DF or YF, right, which is equals to 0.87 Fy into AST. So by equating this, you can find out the area of steel, or you can also find out the neutral axis, right? So neutral axis also depends upon YF. So these both are interrelated. So we will discuss based upon the neutral axis, whether it is in flange or whether it is in web. There are categories which we need to discuss, right? So we will discuss it next video. The moment of resistance of flanged doubly reinforced beam depends upon the depth of neutral axis. So if you want to calculate the moment of resistance of doubly reinforced beam, then it directly depends upon depth of neutral axis. Now, as per the depth of neutral axis, we can categorize the beam into two. One is when neutral axis is within the depth of flange. When the neutral axis is within the depth of flange, and when neutral axis is within the web. So one is the case where it is in the web. Now remember this diagram. This is what we are calling it as. This is flange, and this is web. So when neutral axis is within the flange, when the neutral axis is this is df, and we are trying to make out x here. So from where it is. Now if neutral axis is within the depth of flange, we can say this section as a rectangular section, or in our case we should call rectangular doubly reinforced section. When neutral axis is within the web, your beam will behave as a T section, which is the neutral axis in the web. So by again comparing with limiting neutral axis, you can categorize into three sections, that is over reinforced, under reinforced, balanced section, and over reinforced. Under reinforced section is a section when you compare the neutral axis and with the limiting neutral axis, right? Your neutral axis is within the maximum neutral axis, whereas balanced is both of them are equal, and this is less. So for over reinforced, your neutral axis is more than x. So based on this, and the clause which we are going to follow in this section is G 2.1, again which refers to G.1.1 A, B, C and D. These are the clauses which we need to refer when neutral axis is within the web. Whereas when the neutral axis is in the web, then you again have to categorize based upon the as per the IS code, right? So the first section which we would like to discuss is under reinforced, like the same compared to the XMX. Under reinforced section we have. Under reinforced section is section where neutral axis is within the limiting neutral axis. When you are using this, right, the reference clause is different, and the clause says you need to compare the df by xu ratio whether it is within the limits of 0.43 or not. Right? The second clause is greater than. And there is another section, that is balanced section. I said when balanced section comes, Xmax will come rather than Xm. So in balanced section again we need to compare another ratio, that is df by d less than or equals to 0.2 or df by d greater than 0.2. This last section, that is over reinforced section, shall be completely redesigned. That is what the code says. Avoided and it should be redesigned. The clauses which we use in the analysis purposes for under reinforced section, the clause which says talks about the G.2.3.1, and this clause is specified in G2.2, 2.2.1. There are two clauses which we can refer. Right? So the only extra term which will be added in doubly reinforced section is addition of this extra reinforcement that makes it the value of FSC ASC, which we have discussed in doubly reinforced section. Now you will calculate the AFSC based upon ultimate strain in the steel in compression. Now this value as per code it is given by 0.0035 XU minus D dash by XU. So again this is dependent on XU. So entire moment of resistance calculation of for a doubly reinforced flanged beams is dependent on based on assumption of control axis. We will do one problem, you will understand. For the given section, we need to calculate the moment of resistance. Here you can see a reinforcement in compression sign and tension sign. So, in order to calculate the moment of resistance of this section, we need to go trial and error method. First, we will write down the sectional details. Then we will start calculating the moment of resistance by trial and error. Sectional details are breadth of flange equals to 700, effective depth equals to 900 mm, depth of flange equals to 90, breadth of web equals to 240, and you also given with this D dash which is nothing but 40 mm, and AST, that is 5 into pi by 4 into 25 square, and ASC, that is 3 into pi by 4 into 25 square. ASC is given by 1472.6 mm square, and AST is given by 2454.37 mm square. Knowing these values, you need to calculate the moment of resistance. Okay, so calculation of moment of resistance. So in first trail 1, we will assume that the neutral axis is within the flange. when the neutral axis is within the flange, we have to design this section as a rectangular doubly reinforced section. For a rectangular doubly reinforced section, assuming neutral axis lies within the flange, hence for a doubly reinforced rectangular section, as because we are saying that XU is within the flange, right? The equating compressive forces and tensile forces, you can get this value as 0.36 FCK BF into XU plus the force due to compressive steel, that is FSC ASC equals to 0.87 Fy AST. Now substituting the terms, now you need to calculate FSC. Now assuming FSC and 0.87 Fy, we will take less value rather than 0.87 Fy. So that is 0.87 Fy. Okay, we will write here FCK given here is 20. 15 Newton per mm square. Fy equals to 415 MPa. So Fy, if you multiply, you will get a value of 361 MPa. So let us assume a FSC value of approximately, you can take any value, I am taking 350 Newton per mm square. Now substitute FSC value in here, therefore 0.36 into 15 into 700 into XU you need to calculate plus 350 into ASC equals to how much? You got 1472.6 equals to 0.87 into 415 into AST is 2454.37. Calculate this value, you will get XU equals to 98 mm. Now, if you compare with DL, this 98 value is more than J value. So, which means your neutral axis is lying in web. Right? Now, when neutral axis is lying in the web, right? Now you need to consider this section as a TB. Now this equation will no longer be useful when you are assuming this beam as a TB. This is only for rectangular beam. Now again, so let us consider YF, right? Now we know YF equals to, you always start the trail with assuming the YF is given by 0.15 XU plus 0.65 DF. Now if you happen to calculate this value for the previous neutral axis value, always calculate YF with the previous neutral axis value. 0.15 into XU is how much? 98 plus 0.65 into DF is 90. For F you will get a value as 73.2. So which is again less than DF. So why we have calculated DF? If you happen to calculate the moment of resistance of a flange beam as per clauses G 2.2.1 and G 2.2, there exists a value DF or YF. Whether you have to take DF or YF depends upon the value of YF. right? So we will start with YF, and YF again depends upon neutral axis. We will take the previous neutral axis value, we will calculate YF, and we will substitute by equating compressive forces and tensile forces. Equating compressive forces and tensile forces we will get as, right? Please attend, listen very carefully. This is long equation, but I'll keep it as simple as possible. First term is 0.36 FCK, right? Rather than BF, now you will get BWXU. This we have completed. Now comes the T beam top portion, the balance portion, right? This portion is given by BF minus BW. For that, the force is 0.45 FCK BF minus BW. YF we are taking it, right? Assuming that the neutral axis is more than dm by xu or 0.43. Now, not just that, you have compressive reinforcement also. We have FSC AAC, which is equals to 0.87 F by AST. This is the equation. Now we will substitute all the values. 0.36 FCK is 15 into BW is 240. XU you need to calculate plus 0.45 into 15. BF is 700 minus 240 into YF we know value as this. We will substitute as it is 0.15 XU plus 0.65 into DF is 90. YF we have substituted plus FSC, keep it like that only. FSC into ASC we have got value as 1472.6, which is equals to 0.87 into 415 into AST as 2454.57. Now simplifying this equation, right? You will get this equation as XU equals to 485.45 minus 1.015 FSC. Now XU is dependent on FSC. Again FSC is again dependent on the neutral axis. How? If you happen to recall the calculation of FSC from doubly reinforced beam, FSC can be calculated by calculating the ultimate strain in the steel compression, which is given by 0.0035 into XU minus D dash by XU. Now how much should I take XU value? Now we always say we have to take the previous trial XU value and we will substitute and we will calculate the FSC value. So as per our problem, the previous XU value we have got as 98, right? So we will substitute 98 here. 0.0035 98 minus D dash is how much? It is 40 divided by XU is 98. Now you will get this value as 0.0035 0, 0 to 1. So from stress strain diagram of steel, right, for epsilon SU equals to 0.0021, FSC can be written as 328 Newton per mm square. Now getting the value of FSC, we will back substitute in XU. Therefore, XU equals to 485.45 minus 1.015 into 328 will give you a XU value of 152.53 mm. Now from trail 2, right, we have got a value of XU equals to 152.53. Now we will repeat the same steps from trail 3, that is calculating by F. If by F is greater than DF, then you have to substitute DF here. So entire equation, this equation will changes. So that is why YF is the first thing we need to calculate. So YF is calculated as 0.15 XU plus 0.65 DF. We will take previous XU value and we will calculate it. So 0.15 into 152.53 plus 0.65 into 90 will give you a value of 81.40, which is again less than DF. So as because less than DF, this equation is valid, which means whatever equations we have written here, that is valid. If it is this value is greater than DF, then here DF will come. So this entire will become DF too. So this equation is we have to change. So when you note that this is less, then you can immediately calculate the strain, or you can immediately say, therefore, neutralize is there. We can write down this equation only, 485.45 minus 1.015 FSC. Now after this, what are the steps we have calculated? Again we need to calculate FSC, which is again dependent on epsilon SU. Epsilon SU is given by 0.0035 into XU max minus D dash by XU. So this is given by 0.0035. So previous trail XU value is 152.53 minus D dash is how much? 40 divided by 152.53. Now this value you will get as 0.0026. Now from, again you have to write down from stress strain curves of steel you can draw that for epsilon SU 0.0026 FSC value is given by 0.965 into Fy divided by 1.15. So FSC equals to 0.965 into 415 divided by 1.15 will give you a value of 348.24 MPa. Now after calculating FSC, again back substitute in XU in order to get neutralized step. For trail 3, XU equals to 485.45 minus 1.015 into FSC is 348.24. You will get a XU value as 131.98 mm. From trial 3 you have got XU value as 131.98. Now we will go for trial 3. We need to calculate YF, then we will calculate ultimate strain, then FSC, then we will substitute it. So YF equals to 0.15. Previous total axis is 131.98 plus 0.65 into DF is 90. You will get a value as 78.3, which is again less than DF. So hence this equation can be used. So next, calculating the ultimate strain value in steel, that is 0.0035 into 131.98 minus 40 divided by 131.98, 0.0024. For 0.0024, FSC value is given by 0.95 into Fy by 1.15. If you substitute Fy equals to 415 MPa, you will get FSC value as 342.83 MPa. Now, as because you have got FSC, you can substitute here. You will get the trial 4. XU equals to 485.45 minus 1.015 into 342.83, which is equals to 1. That implies XU will get a value of 137.948 mm. Now you can clearly notice that in the trial 1 we have got a value of 98, in trial 2 we have got as 152, then it has increased, then decreased, then increased. So wherever there is a change in the pattern, right, you can note that you can take this value as, so we can take near about 130, right? Hence XU can be taken as 130 mm from previous trails. Now we need to calculate XU max. XU max for Fe415 steel, it is given as 0.48 times D from page number 70. 0.48 times 0.48, 288 mm. Now, as because that implies when you compare XU with XU max, as because XU max is more, this section is under reinforced section. When it is under reinforced section, we need to calculate the ratio dm by XU as per code number G2, as per clause number G2.3.1. So df by XU, df is given by 90, XU we have taken a value of 130, which give you a value of 0.692, that is greater than 0.2. When the value is greater than 0.2, then we have to consider YF rather than DF. Moment of resistance now is given by now refer clause number G 2.2.1, right, where X max we are not taking, we are taking at XU because it is under reinforced section. For this, MU is given by 0.36 into XU by D into 1 minus XU by D into FCK BW D square plus, now we have got 0.45 FCK BF minus BW into YF into D minus YF by 2. You have another curve in compression. This is in compression, this is compression. You have compression, another force which is in compression for W reinforced section, that is FSC into ASC. For this XU value, we also know, for this XU value, we need to calculate FSC, ASC and YF also. When XU equals to 130 mm, YF equals to 0.15 XU plus 0.65 DF, and if you substitute this value, you will get YF value as 78 mm and epsilon SU as, epsilon XU is given by 0.0035 XU minus DH by XU. Now XU knows, when you calculate epsilon SU, you get as 0.0026. For this, if you happen to calculate FSA, you will get as 348.24 MPa. Do it for your practice. That implies MU equals to 0.36 into XU is given as 130 by D is 600. 1 minus 130 by 600. FCK is 15 into 240 into D square, 600 square plus 0.45 into 50, 700 minus 240 into YF 78 into 600 minus 78 by 2 plus FSC 348.24 into ASC. So we have applied the move or lever arm, that is D minus D dash, into ASC. ASC is 1472.6 into 600 minus 40. And if you calculate this, you will get a value of 514.93 into 10 power 6 Newton mm, or 514.93 kilonewton meter. Now this is the way you need to calculate the moment of resistance of doubly reinforced TB by assuming the neutral axis length. In the next problem, we will discuss about design of doubly reinforced TB. We will discuss about design of doubly reinforced TB. In the previous problem, we have discussed about the calculation of moment of resistance of doubly reinforced beam. Now we are going to discuss about the design itself. In the design, the area of steel is not given. You need to calculate the area of steel. So for these kind of problems, you need to again recall the design steps which we have discussed in the T-beam design. So design reinforced T-beam if the moment applied is 300 kilonewton meter, the moment C, the moment values are increasing. In the analysis of or in the design of rectangular beams, the moment of resistance is near and about 50, so 70, something like that. Now in a doubly reinforced beam, it went to 170s, 150s, or within 200, less than 200. Now when you come to doubly reinforced T-beam, now the movement becomes 300 value. So the changes in the values will definitely tell you the how much, which section should be picked based upon the applied movement. So design a reinforced T-beam if the applied movement is 300 kilonewton meter. Assume M20 grade concrete and Fe415 steel. And the values of this beam are now Vf is given as 750. I am not going to write those things. So 750. This is 90. This is 250. And from center of tensile reinforcement to extreme, the effective depth is given as 500. Fine. Now you got here the ASC. You need to calculate ASC, and you also need to calculate ASC. So that is it, right? So you are given with M20 grade concrete and Fe415 steel as the materials. So BF equals to 750 mm, DF equals to 90 mm, small d equals to 500 mm, BW equals to 250 mm. And as because D dash is not given to you, D dash is the cover, top cover, right? So D dash we can assume it as 50 mm. Okay. If it is not given, you can assume. Now let us go to design calculations. The design calculations of T-beam and this doubly reinforced T-beam is same to same. We need to assume the neutral axis length, and then we have to calculate mu1. If you remember the steps. Neutral axis is assumed within the flange, and we have to calculate mu1. And if mu1 is more than the moment applied, right, then we say the neutral axis shifted. So the same procedure will be followed here. Now in the design calculation, as I spoke about the design moment, we will talk about now what is the design moment. So in the problem, the moment is given as 300. So this should be multiplied with a factor of load factor of 1.5 as per the use of design. So 1.5 times 300 we get as 450 kilonewton meter, right? So in the first step, we will assuming the neutral axis is in the neutral axis is within the flange. So we know that the moment of resistance, right, is given by, for rectangular section, 0.36 FCK. This is stress into BF into XU, and because we are saying it is a flange, we have to take BF multiplied by lever R, that is 0.42 into XU. So as because neutral axis is within the flange, we will assume that XU equals to BF. So we will denote that moment of resistance as mu1, 0.36 FCK BF DF into D minus 0.42 df. Now 0.36, FCK is 20, df is 750, df is 90, d is 500 minus 0.42 into 90. You will get a value as 224.6 into 10 power 6 Newton mm or 224.6 kilonewton meter. Now design moment is 450, so therefore MU1 we should compare with MUD. So as because MUD is more, your neutral axis is not anymore in the flange, neutral axis has shifted down towards the web, right? Hence neutral axis lies in flange. Now when the neutral axis is in the flange, we will assume that df by xu is equals to 0.43, which implies xu is given by df divided by 0.43. So this is given by 90 by 0.43, 209.3 mm. Now before substituting the equations which are given in clause number G 2.2.1 or 2.2, we need to also calculate the ratio df by d. df by d, df is 90, d is 500. This gives you a value of 0.48, which means it is less than 0.20. When it is less than 0.20, you can take df instead of yf. So we will use clause number G 2.2, right? But this is a doubly reinforced section. Remember, you will get another term in compression. So referring clause G 2.2 and substituting xu in place of xu max, you will get as 0.36 xu by d into 1 minus xu by d into fck b w d square plus 0.45 fck bf minus bw into df into d minus df by 2. So in the design calculation, the first part we will assume this entire beam as a rectangle section, then we will calculate the moment of resistance, and then the extra movement whatever we are getting out from here, we will design for doubly reinforced. Okay. So if you happen to substitute all the values here, xu you know, xu as 203 and d as 500, this is 20, this is 240, then let us take this as mu2. mu2 value you will get as 339.35 kilonewton meter or 339.35 into 10 power 6. Now comparing mu2 with MUD, MUD is more. Hence, we can now say that a doubly reinforced beam is a doubly reinforced section is needed. Right? Now we will design of doubly reinforced section is done by, now recall the design steps which we have done when we are doing doubly reinforced beam. So we will first calculate AST1 by equating the compressive forces and tensile forces. Okay. Number 1. Calculation of area of steel in tension, that is equating total compressive forces and tensile forces, you will get as 0.36. For T-beam we have to do it. For 0.36 FCK BW XU plus 0.45 FCK BF minus BW into YF or DF. We have to take DF here. DF equals to 0.87 FI AST. And from this, if you substitute 0.36 into 20 into 240 into XU value is how much? 209.3. We will take 209 plus 0.45 into 20 into 750 into 250 into 90 equals to 0.87 into 415 into AST1 units. Now AST1 is given as 2122 mm square. Now after calculating AST1, right? Now we need to calculate FSC or calculation of area of compression reinforcement. Area of compression steel. Area of compression steel can be calculated as by calculating FSC. So before doing FSC, we need to calculate ultimate strain in steel in compression, which is given by 0.0035 into XU minus D dash by XU. So this is given by 0.0035. Minus 50 divided by 209 will give you a value of 0.0027. For epsilon SU equals to 0.0027 from stress strain relationship of steel, FSC can be calculated as 0.976 into Fy by 1.15. So FSC equals to 0.976 into 415 divided by 1.15, which gives you a value of 352.21 MPa. Now, if you know FSC, then you can calculate ASC from code book as design moment minus movement of resistance divided by FSC into D minus D dash. That implies ASC can be calculated as design moment is 450 minus movement of this beam is 339.35 into 10 power 6 Newton mm divided by FSC is 352.2 into D is 500 minus 90. Sorry, D dash is 50, right? We have assumed 50. That implies you can calculate as 698.13 mm square. Next, AST2 from code book you can calculate as FSC ASC or ASC into FSC divided by 0.87 FY, which is given by ASC we have calculated as 698.13 into FSC as 352.21 divided by 0.87 into 415. Now AST1 total is given by AST1 plus AST2. If you happen to add AST1 and AST2, then you will get AST as 2803.4 mm square and ASC as 698.13 mm square. This is how a doubly reinforced T-beam is designed.